So, as a review, we had something like, let's say in reality, it's a coaxial transmission line, which we'll look at in more detail. So this is, the inner conductor, and this is the outer conductor. And then it goes to something. So this is, the receiver. And this is the transmitter side. So we can use a really simple model of breaking this into chunks of small, really, really small chunks of inductors and capacitors. And these are really, really small chunks. We're calling this distance delta z and looking at the limit as delta z goes to 0. So imagine if you had I don't know how to describe this, but let's say if you had a centimeter long transmission line, you would, divide it down to a billion or, whatever it is, right? So you divide it down and you kind of look at the effects of that. And looking at it that way, what we saw was the equation that sort of defines how if you launched a waveform into one input of this thing, how it would basically travel through is it would go as a traveling wave. So a traveling wave equation worked for this, meaning that you would launch, if you launched a wave on the, say, how should I draw this? That as time, so this is, if I look at the coax as just something like this, and I launched a wave like this, and this was time t is equal to 1, at some other time t is equal to 2, this thing would be traveling down this thing. So it would move over in time with the assumption of just a lossless transmission line. It wouldn't change its shape. You just sort of launch it into this coax, and it would travel down the coax with time. That's the idea of a traveling wave. So it's capable of doing that. Okay, that's what the equation showed. Okay, and that any kind of a form of some function being a function of t minus square root of LCZ or f of t plus square root of LCZ, really any function of, let me just be more general, any function that you'd have like a constant of, let's say, what would be the constant? It would be like omega t minus beta z or omega t plus beta z would be able to satisfy this traveling thing. So that means I could launch, I drew like sort of a sine or cosine wave in this, but I could draw any kind of wave, and it would just, that would be the shape of this wave would be the f. As long as the inside of this function was this formula, then you would have a traveling wave. Okay, and this is satisfied by our transmission line. Okay, and then depending on if the sign here is minus, if I define z direction being positive z direction being that direction, if this is a minus, then the traveling wave is traveling in that direction. If it's a plus, the traveling wave is traveling in that direction. So it means both types of travel in this media are possible or allowed. The equations say you could either launch a wave on one side, send it to the other side, or you could launch a wave from the other side and send it back in the other way. That's what it says. Both are possible in this media. Okay, so that was the one thing we learned. The other thing we learned is that whenever you have a situation where you have a traveling wave, there is a delay between one side. If you're launching something in this and it's traveling to this side, there's a delay associated with that. You launch it, and a certain time later, it'll show up on the other side. So that means there's a transmission line has a delay. Mainly a lossless transmission line has two things, a delay and a characteristic impedance. And if you have this delay, you have the delay because there's a certain velocity of travel of this line. So it's a traveling wave, it's traveling with a certain velocity, and that so-called group velocity is, in a lossless transmission line, is defined as 1 over square root of LC. And there's also a characteristic impedance associated with this. And characteristic impedance says what the wave I'm launching into this thing is typically a voltage wave. Like, when you guys use a function generator and a coax cable, the function generator, you're saying, okay, give me this voltage, it's a square wave or sine wave or whatever it is, a voltage wave. But with that voltage wave, there's an associated current. And the ratio between the voltage and the current waves is what gives you the characteristic impedance, or you want to think of it the other way. So this is given by square root of L over C. Okay, so these two equations, okay, there's very few equations you guys should memorize forever and ever. Okay, these are two of them. Okay, so etch it in your brain, don't forget it. When you're retired, you can forget it. I'm retired, I still remember them. So, just these are really important equations. They're very specific to lossless transmission lines. And later today, we'll hopefully look at what happens when you have a lossy transmission line. Lossless transmission line means we're ignoring the resistance for the time being, just because it makes the equations complicated, and it's easier to talk about a lossless transmission line and then clamp on the lossiness in a little bit to see how it changes things. Okay, but just remember that, especially the characteristic impedance, square root of L over C. Remember that. Are you guys having a hard time reading my writing? Yes.
The square root one on the top, is that a T or an F?
Neither one. It's one. Yeah. Thanks, guys. So please let me know when you're having a hard time reading this stuff, and you will. And these are so common, by the way, that this is let there be light of electromagnetics. So it's not like if you miss it in my thing, is this characteristic impedance, and the phase velocity is something you'll see over, and you go open up Wikipedia, you'll see it. It's just over and over and over again, blogs, websites, whatever. But by the way, when you're being a practicing engineer, so I'm using an example of a coax here, it's pretty unlikely it's coax. The reason I use the example of a coax, because at least when I was your age, or I was familiar with a coax because we had them in the lab, and we had a cable going to the house and so on. But it's very unlikely you guys will be designing coaxes. Very unlikely, unless you're in the wire business. Okay, which is possible. But you're very likely to be designing printed circuit boards. At least that's a lot of people I know, a lot of people I associate with, they design printed circuit boards, and you'll be designing transmission lines in those printed circuit boards, okay? And so the transmission lines in those printed circuit boards, we discussed those. Those are things like microstrip line, they're like the different types, okay? There's like 3 different types of transmission lines having to do with how you lay those out, the thicknesses of the boards, the thicknesses of the metallization, all that stuff. And so what typically happens a lot of times, people have the places that make, how many people have designed printed circuit boards? I keep asking that question, or at least familiar with them. You've designed it. Anybody else designed a printed circuit board? Are you guys generally familiar with printers? You've seen them, right? These are the boards, they usually look green or red or something. So a lot of places make them, and then when you're designing the board, a lot of the vendors, they have these helpful pull down tools where you say, okay, like what if you have this width of a line and this type of transmission line, it gives you the characteristic impedance and the group velocity, because it's so easy to calculate, right? But they just know what the L and the C are for their particular process. Because for a particular printed circuit board, so I'm saying this equation is very common, but what's different from design to design or from manufacturer to manufacturer, and maybe from even layer to layer of your printed circuit board, is what is the particular values of L and C. Because that depends, like the C depends on how thick your dielectric is between layers, and you know the L has to do with the width of the metal and all that stuff, okay? So but in practice what you would do is you'd go, okay, for this line in my printed circuit board, I think it's fast enough that I need to worry about transmission line effects. You go, okay, you go to the manufacturer's site, usually they have that. If they don't, there's other blogs and stuff that you can, if you get the cross section from their manufacturing, and you go, okay, I want to do like a 50 ohm or 100 ohm or typical characteristic impedances, and you pull those down and it tells you the width of these lines, how you should design it. Okay, so in practice, that's what kind of happens. So very useful equations. But again, L and the particulars of the L and the C are what will be different between different media that you'd use. What else do I want to say about this? Okay, so the other thing I want to say about the L and the C, so maybe I'll insert a page here. So this L and C, so I'm going to go backwards in time here. L and C are inductance and capacitance per unit length. Okay, they're not the inductance and capacitance of the whole line. They're given in, so L is given in henries, which is the unit of inductance per meter, and C is farads per meter or microfarads per meter. They're per unit length, okay, because we're defining it. We don't know how wide your transmission, how long your transmission line is. Okay, so that's a review of what was, like for the details of this stuff, I suggest you guys look at hopefully my recording. Hopefully it'll make some level of sense, but that's the majority of what we talked about. The last thing that I wanted to also mention as part of the review was there is this notation. So by the way, Z0, this characteristic impedance, is V0 over I0, which is the voltage wave divided by the current wave, which gives you the impedance, okay? And for our lossless transmission line, that's again, it's equal to square root of L over C. So it's the same guy here. But the full definition of characteristic impedance for a general transmission line is the ratio between the voltage wave and the current wave going in a particular direction. Okay, either If we talk about the voltage wave going from left to right, the normal sign we use is V0 plus, I0 plus. If it's the voltage and current wave going from right to left, it's V0 minus over I0 minus, but in either case, they're gonna be the same value, and it'll be the characteristic impedance. Gives you the characteristic impedance. Hold on, those ratios. Okay, so lastly, what we talked about was a phasor notation that we're gonna use a lot. And again, this is not some like new discovery or some new thing I'm giving you guys. It's just a notation we use to make or it's commonly used to make the calculations easy. So what it is, if you have a voltage or current that is some function. So let's say it's some exponential function. So let me make sure I'm using the right equation, not to confuse you guys. Lecture notes. Let's see, where is my phasor notation? Okay, so let's say that's in the form of V0 plus cosine of omega t minus beta z. And say that's the waveform I've launched into this thing. By the way, can anybody tell me if this is going from left to right or right to left with our notation? Left to right, yeah. And the things that tell you that is that you have this minus sign here, okay? And sort of somewhat helpfully, although this isn't always going to be exactly the case, I'm putting V0 plus here, but it's the sign that tells you it's going from left to right. Okay? This is kind of a little counterintuitive. I don't know why. I think left to right should be plus, but it ends up being minus. The math works out if you do it. So let's say this equation obeys or follows the traveling wave equation, right? The only requirement for a traveling wave equation is that the inside part has this type of this omega t minus beta z, like omega could be anything, beta could be anything, like constant sort of, but this t minus z type of function, that means it's a traveling wave. That means if I keep going from t equal to 1 to t equal to 2 to t equal to 3, whatever, it looks like a waveform that's traveling in distance, in z. The peak of that waveform, if you plot the peak of that waveform as a function of distance, as I clock up the t's, it looks like it's traveling from left to right, just the way the math looks. In this particular case, the function is a cosine, means I've launched a cosine into this traveling wave, but it could be a square wave with a really complicated equation, could be really anything. But as long as the inside has that form, it means it's a traveling wave. And as long as it's a minus sign, it means it's a traveling wave going from left to right in our convention. Okay, so and then this says this is the amplitude of my cosine. The V0 plus is the amplitude. Okay, so in this particular example, okay, what you can do is you can say, if this is the function, right, I can write this as, alternatively, as the real part. So let me work backwards. Let's say if I have, knowing that I want to get to this, okay? Let's say I have a function V0 plus e to the j omega t minus beta z. And that looks like, by the way, I think I mentioned this earlier also, get comfortable with like complex math and equations. So e to the j omega t minus beta z is equal to cos of omega t minus beta z plus j sine of omega t minus beta z. Okay, I have to constantly, this is not something I use a lot, so I have to like refresh myself. So if this thing looks like just this part of this. Okay? So I can write this as V0 plus the real part of e to the j omega t minus beta z. I'm just doing math. Okay? And so in the phasor notation, what they're trying to do is to stop keeping track of omega t and stop keeping track of this real part business. So in the phasor notation, so for a phasor notation, instead of Vz of t, I'm going to call it V hat as a function of Vz and t. And then usually they don't add the z and t in the V hat either, but I guess it's not really a function of t. It'd be V hat z, because it's no longer a function of t. I'm going to drop the e to the j omega t and the real part. So it ends up being V hat e to the minus j beta z. That's the phasor notation. So all it means is for the time being, I'm going to drop this for the time being. I'm going to drop that, and I'm going to drop this real part thing, do all my calculations without those keeping track of what's the real part and what is j omega t, do all my calculations, and at the end, because this is, the phasor notation doesn't really mean anything, the real waveform is this guy. At the very end, after I'm done with all my calculations, I'm going to then plug this e to the j omega t and the real part back in to get the waveform, to get the result that I'm looking for. Do you guys, does that sort of, it's kind of a hard thing to describe because it's not, it's just a notation method of making math a little simpler. And you'll see what I mean when we start doing the math, but you'll start getting confused about what's the phasor, what's the real one, and you can always come back to this description of what we're doing with the phasors. Okay? So that's just where we ended up being. Okay? So what we described is a transmission line, and again, the transmission line has a characteristic impedance and a delay through it. Sorry, guys, this is, give me 1 second. I'm like, not, okay, I know what to do. My email is acting up and is being really annoying. Okay, I know. Okay, so what we looked at, so any questions about that, guys? No? And this is, so far we've looked at lossless transmission lines. So again, no resistance. And so this is for, this transmission line, I've looked somewhere in the middle of this transmission line, put in a bunch of inductors and caps. So imagine this is a cable coming to your home, giving you whatever TV or internet, and I've looked somewhere in the middle of the line, okay? But when you look at any kind of transmission system, you also have a place where your transmitter is sitting at and a place where you're receiving, right? So in the example of the internet cable or your TV cable, the receiver would be your home, would be your whatever cable box, that would be the receiver, and the transmitter would be probably like either some base station somewhere that's transmitting the stuff, okay? So the next step we're gonna do is to see for a transmission line, what happens here and what happens here. So all you need to do for figuring out what happens here is keep track of the characteristic impedance and the delay. Okay, those are the only things you need to know, what happens in the middle. It gets complicated, but theoretically, that's all you need to do. Just keep track of these things. And so we need tools to figure out what happens when you get to the end and what happens at the beginning. And that's what I'm going to talk about right now. Okay, so let's talk about what happens at the end first. So at the receiver. So let me adjust this thing, keeps getting, no, give me 1 second, let me plug my computer in.
Modern school.
What's that?
Modern school.
Modern school, yeah. This thing is really great, but it just keeps going to sleep fast. But the battery life is just awesome. Anyway, so, okay. So the end, the receiver, your home for the cable box, right? Or let's say you're in the lab, it's usually the oscilloscope, okay? Wherever this thing is ending. And so it's called the termination in the characters, for a transmission line. Termination is a word you'll hear over and over again. People ask, what is the termination on that transmission line? Okay, which is a very, very important phenomenon, okay? Because what happens is, imagine this wave traveling through space, okay? Hits the end. What happens there? What's that?
Maybe a reflection?
Maybe a reflection, which is a bad thing. So now I talked about transmission line being a special case of electromagnetic wave. Another electromagnetic wave is light. Okay, so when I have a light, let's say I have a laser, right? I have a laser pointer. It's an electromagnetic wave. And I'm launching it, let's say I have a laser pointer right now. I'm shining it to that window. Okay, so it's moving, it's going in towards the window, and when it hits the window, we're all familiar with a certain part of it goes through the window, and a certain part of it gets reflected back. Okay, so that's kind of the thing that happens in a transmission line. Is when you, in this particular case, there's a termination and then there's a continuation, okay? But it's a reasonable example. Now imagine I have a situation where I have somebody in that building, and I don't know how far that building is, it's, I don't know, 700 meters away or something, okay? In that window, and I'm gonna communicate with them with Morse code or something with my laser pointer. I'm gonna flash on, off, send help to students who are revolting or something. Right? And so I want the light from my laser pointer